In this module, we shall start from the drawback of Pearson product moment correlation coefficient as a measure of association. Then we shall introduce the concepts of concordance and discordance, and hence provide the measure of Kendall's tau as a distribution free measure of independence or say dependence. In our next part, we shall discuss estimation of Kendall's tau in terms of U statistic and provide some properties. Lastly, we shall discuss how Kendall's tau can be used to test for the independence of bivariate samples. And lastly, we shall provide a distribution free test to identify the presence of trend in data, which is known as Mann-Kendall test. We start from the association measure in the context of parametric inference. Suppose we have n pairs of data xi, yi from a continuous bivariate distribution defined by fxy. Suppose the objective is to get some idea about the nature of dependence between x and y. The most frequently used measure in this context is the Pearson correlation coefficient defined by the ratio of covariance between x and y and the standard deviation of x and standard deviation of y. Rho is a scaled measure of degree of linear association and the direction of association. A large positive value, of course less than unity, indicates that large values of x are paired with large values of y and vice versa. Although rho is well accepted as an association measures, but it suffers from a number of drawbacks. First of all, it is a measure of linear dependence between x and y. That is, if the actual relationship is actually or at least approximately linear, rho is a good measure. But if the actual relationship is far from the linearity, rho gives misleading results. For example, suppose x has a normal 0, 1 distribution, then the covariance between x and y, where y is defined as x square, is 0. That is, rho equal to 0 in this case, and hence there is no linear relationship between x and y. Then x and y are uncorrelated, but there is actually an exact quadratic relationship. So rho heavily depends on the existence of the first few moments of the underlying distribution. As we can recall that the definition of rho involves covariance between x and y, variance of x and variance of y. So the dependence on the first few moments is clear. Lastly, the value of rho remains unchanged if the underlying variables are replaced by some linear functions with positive slope. That is, if the transformation is linear and order preserving, then rho does not change. However, if the transformation is non-linear but order preserving, the value of rho may change. So next we shall discuss or introduce the concept of concordance. In order to get invariance under order preserved transformation, we must depend on relative magnitudes instead of absolute magnitudes. Thus, we define the concepts of concordance and discordance. Consider two pairs of observations denoted by xy and x dash y dash. These pairs are concordant or in agreement if they vary in the same direction. That is, if x less than x dash whenever y less than y dash, or if x greater than x dash whenever y greater than y dash. Next, we shall introduce the concept of discordance. Consider the same pairs of observations xy and x dash y dash. These pairs are said to be discordant or in disagreement if they vary in the opposite direction. That is, if x greater than x dash whenever y less than y dash, or if x less than x dash whenever y greater than y dash. In other words, if the line joining these points has a positive slope, the points are concordant and discordant otherwise. Naturally, concordance or discordance property is preserved under an order preserving transformation. That is, if we consider some transformation g such that x greater than x dash whenever gx greater than gx dash, then the concordance remains same. So In our next slide, one can see the pictures of concordance and discordance. Actually, concordance is indicated by a straight line with positive slope, and discordance is indicated by a straight line with negative slope. So what are the concordance and discordance probabilities? The probabilities of concordance and discordance are invariant under order preserved transformations, and hence a measure of association can be developed by the combinations of these probabilities. For any two independent pairs x1 y1 and x2 y2, the probability of concordance is defined as pi c, which is nothing but the probability of x1 greater than x2 and y1 greater than y2, or x1 less than x2 together with y1 less than y2, which can be restated as probability of the product x1 minus x2 y1 minus y2 is positive, or this probability is the same as probability y2 minus y1 divided by x2 minus x1 is positive. Thus, pi c can be looked upon as the probability that the straight line joining the random points x1 y1 and x2 y2 has a positive slope. Similarly, the probability of discordance is defined as pi d as probability x1 minus x2 multiplied by y1 minus y2 is less than 0. Since perfect association is either perfect concordance or perfect discordance, a difference between pi c and pi d measures the extent of association. The difference pi c minus pi d is defined as the Kendall's tau coefficient. If the marginal distributions are assumed to be continuous, then the probability that x1 equal to x2 is 0 and the probability that y1 equal to y2 is also 0. Then we have pi c plus pi d equals unity. Thus, we can express tau as twice pi c minus 1, which is the same as 1 minus twice pi d. Naturally, tau does not depend on the moments of the underlying distributions and hence is always defined. But the converse is not in general true, and hence we get a similarity with rho. However, for a bivariate normal population with correlation coefficient rho, independence is implied by tau equal to 0, and we all know that rho equal to 0 is an indicator of independence in bivariate normal population, and independence tau equal to 0 and rho equal to 0 are all equivalent. So to be specific, suppose xi yi I from 1 2 are IID observations from a bivariate normal distribution with means theta x theta y, variances sigma square x sigma square y, and correlation coefficient rho. Define u as x1 minus x2 divided by sigma x multiplied by square root of 2, and v as y1 minus y2 divided by sigma y multiplied by square root of 2. Then the joint distribution of uv is a standard bivariate normal with correlation coefficient rho. Thus, Pc, the probability of concordance, reduces to the probability that uv is positive, and using the properties of bivariate normal distribution, we get this Pc equals half plus sine inverse rho divided by pi. Then tau equals twice sine inverse rho whole thing divided by pi, and hence we get the desired relation. Next, we come to the estimation of Kendall's tau. Suppose we have data, say n pairs of data xi yi, and from a bivariate continuous distribution f. So in order to estimate Kendall's tau, we shall use the theory of u statistics. So we start with defining the sine function as sgn u equal to plus 1 if u greater than 0, equal to 0 if u equal to 0, equal to minus 1 if u is less than 0. Then we observe that the sine of x1 minus x2 and sine of y1 minus y2, that is the product, equals 1 if the product x1 minus x2 y1 minus y2 is positive, and it equals minus 1 if the same product is negative. Thus, the expected value of the product of sines of x1 minus x2 and y1 minus y2 equals the probability of the event that x1 minus x2 multiplied by y1 minus y2 is positive minus probability that the product x1 minus x2 and y1 minus y2 less than 0, which is nothing but pi c minus pi d, and we all know that this pi c minus pi d is defined as the Kendall's tau, which is indicated by tau. So next we shall introduce some another analogy with the Pearson's correlation coefficient. Actually, tau can be expressed as a product moment correlation coefficient. So for this we define Cij as the sine of xi minus xj and dij as the sine of yi minus yj. Assume that xi not equal to yj with probability 1 and yi not equal to yj with probability 1 for every I not equal to j. Then the summation of Cij square and the summation of dij square is nothing but n into n minus 1. Again, the sum of the cross product Cij multiplied by dij is nothing but twice c minus d. Thus, we can write u as summation Cij multiplied by dij whole thing divided by square root of summation Cij square multiplied by summation dij square. Thus, u is expressed as a simple correlation coefficient. So, once we expressed this sample Kendall's tau in terms of U statistic, we can get the corresponding summary measures. Now, from the properties of U statistic, expected value of U is nothing but tau and variance of U can be expressed as twice n minus 2 sigma 1 square plus sigma 2 square whole thing divided by n choose 2. Now, using the theory of U statistic and the notations already defined, phi 1 with arguments x1 y1 is the conditional expectation of phi given x1 y1. Then a little manipulation expresses that expected value, the conditional expectation of the product of sine functions is nothing but 1 minus twice f x1 infinity minus twice f infinity y1 plus 4 f x1 y1. Then sigma 1 square is nothing but variance of 1 minus twice f x1 infinity minus twice f infinity y1 plus 4 multiplied by f x1 y1. However, sigma 2 square is nothing but 1 minus tau square. Hence, for specific choices of f, the variance can be obtained. However, if we assume independence, that is fxy equal to fx infinity multiplied by f infinity y for all xy, then this 1 minus twice f x1 infinity minus twice f infinity y1 plus 4 times f x1 y1 has the same distribution as 4 times v minus half multiplied by w minus half, where v and w are IID rectangular 0 1 variables. Thus, after a little simplification, we find that sigma 1 square is nothing but 1 by 9. Moreover, under independence, this tau equal to 0 and we get sigma 2 square as 1, and hence a little algebra gives the variance of u under independence as 4n plus 10 whole thing divided by 9n multiplied by n minus 1. So, next we come to an interesting application of Kendall's tau, which is known as test of independence. Suppose we have samples from some bivariate population and we are interested in testing independence. That is, our null hypothesis in this case is fxy equal to fx infinity multiplied by f infinity y for every xy against dependence. Now, one can note that this fx infinity is nothing but the marginal distribution function of x and f infinity y is nothing but the marginal distribution function of y. So, for underlying dependence, u tends to be either too large or too small. Thus, too large and too small values of u indicate the strong possibility of dependence. Again, the distribution of u is symmetric about 0 under the null hypothesis. Thus, we reject the null hypothesis if modulus t is too large, and this mod t is nothing but again the distribution of u is symmetric about 0 under the null hypothesis. Thus, we reject the null hypothesis if the absolute value of u is too large. Again, from the theory of u statistic, as n tends to infinity, the large sample distribution of u multiplied by square root of n is normal with mean 0 and variance 4 by 9. Then, a large sample test rejects the null hypothesis if the observed value of square root of 3n by 2 multiplied by absolute value of u exceeds tau alpha, where tau alpha is the upper alpha percentage point of a standard normal distribution. So, after performing a test, suppose we have some data and we are interested to know the strength of the data. So we have to calculate p-values. Suppose small u is the observed value of capital U, then the one-sided p-values are probability u greater than equal to small u under null hypothesis, and we accept the null hypothesis if this p-value exceeds alpha. Again, if our alternative is fxy less than equal to fx infinity multiplied by f infinity y for some xy, then the one-sided p-value is probability capital U less than equal to small u evaluated under the null hypothesis, and we accept the null hypothesis if this p-value exceeds alpha. If we consider testing the two-sided alternative, that is fxy not equal to fx infinity multiplied by f infinity y for some xy, then the two-sided p-value is twice minimum of the p-values obtained earlier. We reject the null hypothesis if this p-value does not exceed alpha. Next, we discuss the effect of tied observations on this Kendall's tau. We have assumed continuity of each marginal distribution function to avoid ties, but in practice ties can occur within either or both samples. However, u is based on the quantities sin xi minus xj multiplied by sin of yi minus yj, and hence assigns a value 0 if a tie occurs. Thus, as before, u remains unbiased for tau even under the presence of ties. However, if we have t ties in x observations of lengths k1, k2, kt and s ties in y observations of lengths k1 dash up to ks dash, then u can be expressed as the ratio summation Cij multiplied by Dij divided by square root of n into n minus 1 minus summation of Ki into Ki minus 1 and whole thing divided by the square root of n into n minus 1 minus summation Kj dash multiplied by Kj dash minus 1. This modified u is often called Kendall's tau b measure. We have discussed so far that Kendall's tau is defined only when PC plus PD equal to 1. That is, the pairs are only concordant or discordant. But if the marginal distributions are not continuous, we have PC plus PD, which is nothing but the probability of concordance plus probability of discordance, which is nothing but 1 minus probability the product yi minus yj multiplied by xi minus xj equal to 0, which is nothing but 1 minus probability that xi minus xj equal to 0 or yi minus yj equal to 0, and which we denote by 1 minus p naught. Naturally, p naught, that is probability xi minus xj equal to 0 or yi minus yj equal to 0, is the probability that a pair is neither concordant nor discordant. Thus, tau is not a sensitive measure of association if p naught is positive. Thus, we define the conditional probabilities of concordance as Pc star, which is nothing but the ratio that probability yi minus yj multiplied by xi minus xj is positive, whole thing divided by probability yi minus yj multiplied by xi minus xj is positive plus the probability of yi minus yj multiplied by xi minus xj is negative. Naturally, this Pc star is nothing but Pc by 1 minus p naught with already introduced notations. Similarly, the conditional probability of discordance is PD star equal to 1 minus PC star. Then a modified association measure can be defined as tau star equal to PC star minus PD star. Since tau star equal to tau divided by 1 minus p naught, we get the corresponding sample version u star equal to u by 1 minus p naught hat, where p naught hat is a consistent estimate of p naught. Since the large sample distribution of u star and u divided by 1 minus p naught are the same, the asymptotic distribution and a large sample test based on u star can be derived as earlier. Next, we shall discuss an application of Kendall's tau in real life. Actually, we shall discuss a test of trend using tau. For data coming from some measurement process often show some trend, that is, observations in general depend on time. In the test of randomness, we have seen that a specific pattern of run indicates the presence of trend. Now, we shall discuss how Kendall's tau can be used to check the presence of trend. Suppose x indicates the time variable and y denotes the corresponding observation. Then an association between x and y might indicate a presence of trend, and this suggests to use Kendall's tau to serve the purpose. Suppose the x observations are time ordered, then the hypothesis of independence of the time ordered observations yi, I from 1 to small n, can be tested through tau. In such a case, we take xi equal to I running from 1 to small n, and define the statistic as u, or this u reduces to 1 divided by n choose 2 summation the sign of yj minus yi. Now, u is expected to be higher or lower according as the underlying trend is upward or downward. Thus, we reject the null hypothesis of the absence of any trend against the presence of an upward or downward trend if u is too large or too small. Note that the null distribution of u is the same as before. Thus, we have derived a distribution-free measure of association in the context of non-parametric inference. We have enumerated some properties like symmetry, large sample distribution of this measure, and finally we have discussed an interesting application to detect trend in the dataset, and this test is well known as Mann-Kendall test of trend.